We have finished lesson 1 by introducing the concept of probability function. If you remember, before giving its definition, we have guessed what are the properties of such function by using the very simple random experiment of tossing a coin. This gave us the possibility to guess that the probability function should be defined on a set that contains both events and their complementary, their unions and intersection. It also gave us the possibility to guess the properties that the probability function should satisfy, namely, the probability assigned to the whole sample space should be 1, the probability of the disjoint union of events should be represented as the sum of the probabilities of these single events, and finally, the probability of the empty set should be 0. All these guesses appear in the formal definition of probability function, except for the last one, that is, in the definition of P, we don't explicitly demand that P applied to the empty set gives us 0. Why that? Well, because it will be redundant to ask this last property, since it follows from the Kolmogorov axioms 1 and 2, as we're going to see with a theorem at page 12 of the notes. Let's discuss this theorem. For all events E, any probability function P has the following property. P applied to the complementary of E is equal to 1 minus P applied to E. In particular, this implies that P applied to the empty set is 0. To prove the theorem, we just have to remember the definition of the complementary set. The complementary of the event E is the set of outcomes of S that don't belong to E. This is a graphical representation of this. We have the event E, and all the outcomes of S that don't belong to E are contained in the complementary set of E. Hence, these two sets are disjoint, and their union gives rise to S. This implies that we can write a partition of S like this, and so we can apply the Kolmogorov axiom K1 to write 1 equals the probability of the entire sample space equal the probability of E disjoint union with E complementary, and then we can apply the Kolmogorov axiom to write this as the disjoint sum of the probability associated to E and the probability associated to the complementary of E. So we have that P of E plus P of E complementary is equal to 1, and so P of the complementary of E is equal to 1 minus the probability of E. Now notice that we have considered any event E, and so we can also write this formula for the particular event that is equal to the entire sample space. So this becomes P of the complementary of the sample space, and this becomes the probability of the entire sample space. Let's see what happens. We have that the probability of the complementary of the sample space is the probability of the empty set, because the sample space is the universe set, and so it contains every outcome. And if we search for elements that don't belong to the universe, of course, we are left with the empty set. Then here we have 1 minus the probability of the sample space, but the probability of the sample space is 1 thanks to the first Kolmogorov axiom. So we have 1 minus 1, 0. This is the reason why we don't have to demand explicitly in the definition of the probability function that the probability of the empty set is 0, or that the probability of the complementary of an event is 1 minus the probability of the event itself, because these properties are implied by the Kolmogorov axiom 1 and 2. Each time we define a mathematical object, in this case the probability function, we have to check that its properties agree with what we expect. Now we verify if the property contained in the last theorem that we have just proven is consistent by introducing another typical example of probability, that is, a game of cards. Consider a typical deck of cards, then its sample space will be this one, where these letters stay for clubs, diamonds, hearts, and spades. Then let's consider the event E given by CH. This event occurs when we pick a card from the deck that is either clubs or hearts. The complementary event will be DS, which occurs if we pick from the deck either diamonds or spades. If the deck of cards is fair, then half of the cards will belong to E and the other half to E complementary. So it makes sense to assign a probability function P of E equals P of E complementary. Now, using what we have just learned, we have that P of E complementary is 1 minus P of E, but it is also P of E. By considering just this equation here, we have that 2P of E must be equal to 1, that is, P of E must be equal to 1/2, which is also the value of P applied to the complementary of E. This fact implies that we have a 50% chance of picking a card that is either club or hearts on one side, or picking a card that is either diamonds or spades on the other side, which of course agrees with common sense. We are of course very pleased of the fact that we continuously find confirmations of the fact that our proposal from the probability function agrees with what we expect it to do. Let's go further and check another seemingly intuitive property of P. If an event E is composed by less outcomes than another event F, that is, in mathematical terms, E is a subset of F, then the probability assigned to the event E should be smaller than the one assigned to F. We're going to prove that this is indeed the case, but before we have to prove another property of the probability function P. That is, the probability of F intersection with the complementary of E is equal to the probability of F minus the probability of E intersected with F. The proof of this first property is very easy if we consider the so-called Venn diagrams. In this picture, we see the event E and F embedded in the sample space S. I want to prove that we can write F as the disjoint union between the intersection of E and F, that is the set indicated in orange, and the intersection between F and the complementary of E, that is the part indicated in green. To do that, we simply have to draw the complementary set of E, which is this one depicted in red. Then, if you think about it for a second, if you intersect the complementary of E with F, you find the green region. So, indeed, F can be written as the disjoint union of E intersected with F and F intersected with the complementary set of E. Each time we have the disjoint union, we can apply the probability function and use the Kolmogorov axiom K2, and so we have that the probability of F is equal to the probability of E intersected with F plus the probability of F intersected with the complementary of E. If we rearrange the terms, we find exactly the formula that we want to prove. Now we can consider the really interesting situation for us, that is, when an event is a subset of another event. As you can see, once we have established property 1, the proof of property 2 is very easy. The only thing that we have to remember is that whenever E is a subset of F, then the intersection of E and F is exactly E. And you can understand this fact by taking a look at this Venn diagram. So now let's write the probability of F intersected with the complementary of E. Since it is a probability, it is always greater or equal to 0. Then we apply property 1 that we have established before. That is, we can rewrite this as P of F minus P of the intersection between E and F. But since we are in this condition, we can rewrite this as the probability of E. So finally, the difference between P of F and P of E is greater or equal than 0, and so the probability of E is less than or equal to the probability of F. Before, when I introduced the property event E subset of the event F implies that the probability of E is inferior than the probability of F, I said that this is a seemingly intuitive property. In the next example, I explain why I said seemingly. In 1981, the two cognitive psychologists Amos Tversky and Daniel Kahneman introduced what now is called the Linda problem. Let's read together. Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with the issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. Which event is more probable? Linda is a bank teller. Linda is a bank teller and is active in the feminist movement. Now, the great majority of people that answered to this question chose the answer 2, declaring that the description of Linda was more likely to be that of a feminist. However, if we consider the set of all female bank tellers and the set of all female bank tellers which are also feminists, then the second one is clearly contained in the first one. In fact, it is clear that every female and feminist bank teller is also a bank teller, while it is not necessarily true that a female bank teller is also feminist. This very famous example shows that our intuition may lead us to take for granted characteristics that are not necessarily true. As a curiosity, Daniel Kahneman became famous as being one of the few cognitive psychologists who won the Nobel Prize, not for psychology because it doesn't exist, but for economy. If you're interested, I can suggest to read his book Thinking Fast and Slow. Let's now turn our attention to the axiom K2, which says that the probability of the disjoint union of two events is the sum of the corresponding probabilities. Well, can we say something when the union is not disjoint? First of all, notice that if the union is not disjoint and we sum the probability of each event, then we take into account 2 times the outcomes that belong to the intersection. Of course, if you think about it for a second, there's absolutely no reason to count the outcomes in the intersection twice. And to reestablish an equal treatment of the outcomes, we expect that the probability function assigns to a non-disjoint union of events the sum of their probabilities minus the probability of the intersection. The following result, which is an immediate consequence of the previous theorem, says that this is exactly what happens. So, given a probability function P and two events E and F, we have that the probability assigned to the union of E and F is the sum of the probability assigned to E and F minus the probability assigned to their intersection. The proof lies in these Venn diagrams. Here you have the event E, Here you have the event F, and as you can see, they intersect non-trivially. The set represented in green is the intersection between F and the complementary of E. Why is it interesting to consider such a set? Well, because, as you can see, the union of the event E and the event F can be written as the disjoint union of E and F intersected with the complementary of E. Notice that this union is disjoint because we have left the intersection in E, and so the union of this set depicted in orange and this set depicted in green is of course disjoint because there are no outcomes shared by these sets. The fact of writing the union as a disjoint union with another set allows us to apply Kolmogorov axiom number 2. In fact, the probability of this event becomes the sum of the probability of these two events here. Then we can use the property 1 of the previous theorem, and instead of writing this, we write this. The final result that we obtain is that the probability of the union of two events that intersect non-trivially is the sum of the probabilities of the two events minus the probability of their intersection. From this result, it follows that the probability of the union of two events is smaller than the sum of the probabilities of the separate events, because we subtract to this a positive value. If instead of considering just two events, we consider n events, then we can generalize this formula through the so-called Boole inequality. The results that we have just discussed are not only theoretical, in fact, we will show their usefulness in this example. We close this section with a result that will be very useful later when we will discuss conditional probability. This result shows also the benefits of the Kolmogorov axiomatization of probability through set theory. In fact, as we are going to see, the proof of this result is relatively easy, which is not the case if you use other methods. The theorem is the following. Consider a probability function, an event E, and a partition of the sample space. Then, the probability of the event E is the sum of the partial probabilities obtained by considering the intersection of the event with all the sets that belong to the partition. Using a probabilistic language, we can translate this result by saying that the probability of an event E is the sum of the probabilities of the simultaneous occurrence of the event E and the events that belong to the partition. Before showing the general proof, let's consider a two-set partition given by F1 and F2. Then, since F1 and F2 form a partition, they are disjoint, and their union is the sample space S. Then, this equation means that the probability of E is the probability that E occurs simultaneously with the event F1 plus the probability that E occurs simultaneously with the event F2. So you see that when you consider just two sets in the partition, this seemingly abstract formula becomes much more comprehensible. Now let's discuss the proof. First of all, we notice that E can be written trivially as the intersection of itself with the sample space. E is a subset of the sample space, and so this relationship holds. Then we write S as the disjoint union of the sets that appear in the partition. And so we can write that E is equal to E intersected with the disjoint union of the set appearing in the partition. Then we can use the distributivity between intersection and union to bring E inside the disjoint union, like this. Let's now apply the probability function to the first and the last member of this equality. Obtain this relation here. The last thing that we have to recall in order to conclude the proof is that the events Fk are all disjoint, and so also these events here are disjoint. Thus we have a disjoint union, and thanks to the axiom K2, we can write this probability like this. As I told you before, we are not going to use immediately this result, but it will come in handy when we will discuss conditional probabilities.
The concept of probability function will remain with us until the end of this course. This is why I wanted to underline its importance with this short video. The first thing that we have to do in order to construct the probability function is to consider a sample space S where events live, and then to build a set A containing all the events, their complementary sets, their unions and intersections. We then use A as the domain of a function indicated with P that brings any element of A that I indicate for simplicity simply with E to a normalized real value between 0 and 1, like this. This function P is called a probability function if it satisfies the two Kolmogorov axioms that I recalled here. The first one is the easiest to state and interpret. It simply says that the probability function assigns 1 to the entire sample space S, which simply means that whenever we perform a random experiment, we obtain a result. The second axiom refers to incompatible events and says that when we have a bunch of incompatible events, then the probability assigned to their disjoint union is simply the sum of the probability assigned to each single event. Using the Kolmogorov axioms, we have proven 4 properties of the probability function. The first one is that the probability of the complementary set of E is 1 minus the probability of E. The second is that the probability assigned to the empty set is 0, which simply means that there is 0 probability to perform a random experiment and not getting a result. And then we have the probability of the union of two events is the sum of the single probabilities minus the probability of the two events simultaneously, that is, the probability of the intersection between the two events. The final property is very important but also a little bit trickier because it involves a partition Fk of the sample space S. The property says that whenever we have an event E, then its probability is given by the sum of the probability of the intersection between E and all events Fk belonging to the partition.
Combinatorics is the art of counting under constraints, and in probability it is used when we subdivide a job into multiple tasks. Let's immediately see the fundamental theorem of counting that we'll use many times in the following. The theorem says that if a job consists of k separate tasks, the ith of which can be done in ni ways, then the entire job can be done in n1, n2, and k ways. To avoid useless complications, we will perform the proof only for the case k equal 2. The proof can be more easily understood with the help of this picture. When k equals 2, we can subdivide the entire job into 2 tasks, this one and this one. Task 1 can be performed in n1 ways, and for each way we have n2 choices to perform the second task. If you count all the possibilities, you find 1 times n2, as it is written here, plus itself, and 1 times. So at the end, you find that the job can be performed in n1 times n2 ways. If instead of k equals 2 you consider a generic k, then the job can be performed in n1 times n2 times etc. nk ways. Let's immediately put in practice the fundamental theorem of counting with the example of the lottery. Imagine that we have a lottery in which we can extract 50 different numbers. We can distinguish two types of lotteries, without and with replacement. The lottery without replacement is by far the most common. Once a number is extracted, it's removed from those which can appear in the following extraction, and it is not replaced. In other terms, in this lottery, one number can be extracted only once. In the second type of lottery, less common but it exists, the number that has been extracted is placed back to the ensemble of numbers that can be extracted further, and for this reason it is called with replacement. The consequence is that in this lottery the same number is allowed to be extracted multiple times. Since we want to be coherent with the proof just performed, we consider the following job: extract two numbers in a lottery. For a lottery without replacement, this job can be done in 50 times 49 ways. The reason is that there are 50 possible outcomes in the first extraction and 49 in the second. Instead, for a lottery with a replacement, the job can be done in 50 square ways, because we replace the number that has been extracted, and so there are 50 possible outcomes both in the first and in the second extraction. Besides replacement, there is another constraint that must be taken into account when we consider counting, that is ordering. We can illustrate this constraint using again the example of the lottery. Imagine that the winning numbers that have been extracted are precisely these ones in this exact order. Then we can ask ourselves, is a person who selected the same numbers but with a different order qualifies as a winner or not? Of course, the answer depends on whether the ordering counts or not. If it does, then the person did not win. Otherwise, the person won. Mixing together ordering and replacement, we have that there are 4 different ways of counting that we can visualize in this table. Of course, we have to fill the blank spaces in this table by performing the intersection between rows and columns. For example, if we have counting without replacement and unordered, then we have to fill this blank here. In order to fill all the blanks of the table, we need to introduce the very important concept of permutation. If we denote with in the set of the first n strictly positive integer numbers, then a permutation is defined to be a one-to-one and onto function on in. Otherwise said, a permutation is simply an exchange of n labels such that labels cannot disappear or occupy more than one slot. The identity function on in, that is, the function that takes n as input and throws n as output, is of course a permutation, is the easiest possible permutation, and for this reason is called the trivial permutation. A non-trivial example for the set I4 is this permutation here, in which 1 is exchanged with 3, 2 with 1, 3 with 4, and 4 with 2. However, if, for example, you remove this correspondence and you apply 2 to 3, then this is not a permutation. This is because the label 2 occupies more than one slot. For the following, it will be very important to understand how many permutations of n labels can exist. This is actually quite easy to understand, and we have to reason as follows. We start occupying the first slot of the novel set of labels by using one of the previous set, for example, this one here. Since there are n possible choices, we write n here. Now we occupy the second slot by selecting one label that remained available here. But since there are n-1 labels left, the second slot can be occupied with n-1 choices. Since we have selected one label, for example this one here, to place it into this slot, we have to remove it from the initial set of labels. Now you have understood the game. The third slot can be occupied with n-2 choices, etc., until we arrive to the last slot that can be occupied only with one choice. So what did we do? We have decomposed the job of counting all the possible permutations in n tasks, each of which can be performed in n-1, etc., ways, until we arrive to a unique way to perform the last task. As a consequence, thanks to the fundamental theorem of counting, we have exactly n-1, n-2, etc., times 1 permutations. This number has a special name. It is called n factorial, and so n factorial is simply the product of all the positive integers less than or equal to n, like this. Since multiplying by 1 doesn't change anything, the multiplication by 1 is in general bypassed. Moreover, the factorial is extended to encompass 0 by defining 0 factorial equal 1. The factorial grows very rapidly. For example, there are 5 factorial ways to permutate 5 elements, that is 120 ways. However, if you consider 8, then the number is 40,320. And if you consider 10 and 14, you have these very large numbers written here. Before using the factorial and permutation in examples, let me just underline a very important property of the factorial, which is this one here. That is, n factorial can be written as n times n-1 factorial. This is very intuitive. However, let's see a numerical example. You can write 5 factorial as 5 times 4 times 3 times 2, but also as 5 times 4 times 3 times 2, which is 4 factorial. And so 5 factorial is exactly the same as 5 times 4 factorial. Let's now put in practice the factorial with this very nice example. Imagine that a friend of yours invites you to dinner and he or she tells you the 4-digit code that you have to type in order to open the door of the building. Imagine also that when you arrive there, you recall that the code contains the numbers 1, 4, 7, 9, but you forgot the order. How many different combinations of these 4 numbers do you have to test? Well, thanks to the previous reasoning, you have to test 4 factorial, that is 24 different codes. Unless you have a formidable memory, you should write down each code in order to avoid repeating the same by mistake. We can roughly estimate 10 seconds for both actions, that is, typing the code and writing it down. Then, under these assumptions, and in the worst case scenario in which you have to type the code 24 times in order to find out the correct one, you have to spend 240 seconds, that is 4 minutes, before opening the door. Now imagine that the entry code has 5 digits instead of 4. Then, if you repeat the same reasoning, there are 120 different codes, and the worst case scenario now is 20 minutes. Finally, remark that in this example, we have supposed that we recall the digits appearing in the code. If we don't, then we have to select them from the 10 digits from 0 to 9. We're going to see that in this case, the count is much larger. In the next page, we analyze in detail the 4 different cases of counting. To more concretely understand the different types of counting, we will use the example of the entry code as a beacon. Let's start considering the case ordered counting without replacement. In this case, the order of the code digit counts, but the code is supposed to be built from different digits. So there are 10 ways to find out the first digit, 9 for the second, then 8, and finally 7. The fundamental theorem of counting says that we have to multiply all these numbers, reaching 5040. If we use the same time estimation of the previous example, if we have forgotten the different digits that appear in the code, the worst case scenario to enter in the building grows to 14 hours. If we want to generalize the previous computation to a more general situation, we have to modify it using this very simple manipulation that I wrote here in red. That is, we see that if we multiply and divide by 6 factorial, we obtain the fraction between 10 factorial and 10 minus 4 factorial. Why is this expression better than the previous one? Well, because in this novel expression, there appear only 10, the number of digits, interpreted as the number of items that can be selected, and 4, the number of items that we actually need to digit the correct code. And in fact, in general, the number of ways to choose R items from N items without replacement but considering order is this number here. That is the fraction between n factorial and n minus r factorial. Let's consider the second case, in which ordering counts and the digits may be repeated in the code, and so we have replacement. In this case, there are 10 ways to select each digit in all the 4 cases, and so the counting is 10 times itself 4 times, that is 10,000. So, if you have forgotten the code digits and they may repeat, in the worst case scenario, to enter the building, you have to wait 27 hours. Abstracting what we have just said in a more general situation, we have that the number of ways to choose R items from N items with replacement and considering order is n to the power r. Now we consider the case of counting without ordering and without replacement. We can take advantage of the computation performed in item 1, in which we haven't considered replacement, but we did consider ordering. Recall that in that case, what we have obtained is this value here. So in the present situation, what we have to do is simply to divide out the number of choices corresponding to the 4 factorial redundant ordering. This is exactly what I have done here. Numerically, what we obtain is 210, which is much smaller than 5040 found in item 1. In fact, in this case, the worst time delay to enter in the building is 35 minutes. Before generalizing this computation, let me give you some advices in order to compute this fraction. It's always a nice idea to use the previous property of the factorial that I showed to expand the numerator as I did here. Why did I stop at 6 factorial? Well, because in this way I can cancel it out with the 6 factorial at the denominator. So let's remove these factors. We remain with 4 factorials that can be written explicitly like this. And then we can cancel out 8 with 4 times 2. Finally, we can cancel 9 with 3 by removing completely the denominator and remaining with 3 at the numerator. To conclude, we have 7 times 3, which is 21, multiplied by 10, 210. Using this strategy, you can easily compute factorial fractions by hand. Now let's abstract this computation. This number that we have found in mathematics has a specific name. It's called the binomial coefficient. Consider two non-negative integers n and r such that n is larger than r. Then the binomial coefficient is written like this, and it's read n choose r. Its mathematical expression is this one here. That is the fraction between n factorial and r factorial times n minus r factorial. There are some particular expressions of the binomial coefficients that you can see here. As a nice and useful exercise, you can check that n choose 0 is 1, n choose 1 is n, and n choose n is 1. The reason for the name binomial coefficient lies in the fact that it appears in the expansion of the positive integer power of a binomial, this expression here. A pictorial representation of the binomial coefficients is provided by the famous Pascal-Tartaglia triangle. To build it, you start by 1 on the top, and then you add rows like this, which contain numbers constructed in the following way. Each number is built by adding the number appearing in the previous row on its left and on its right. For example, we write 1 here because we consider the absence of a number on its left as 0. So we have 0 plus 1, which is 1. But if, for example, we consider this number here, we have 6 plus 4, which is 10, etc., etc. Finally, to resume, the number of ways to choose r items from n items without replacing and not considering order is given by this binomial coefficient. We have arrived to the final situation, that is, counting without order but with replacement. This is by far the most difficult case to count, and unfortunately we don't have the time to go through all the details that we need in order to motivate the corresponding formula, so we simply give the correct answer. A 4-digit code to be selected from 10 numbers without ordering but considering replacement can be chosen in a number of ways given by this binomial coefficient. As an exercise, you can perform the computation, which gives 715, which in the worst case scenario corresponds to a waiting time of 2 hours. Abstracting what we have said, we have that the number of ways to choose r items from n items with a replacement but without ordering is given by this binomial coefficient here. In the following table, I summarize the enumeration methods.